organizado por OES, capítulo de la rama estudiantil y EEE, y el grupo conjunto con el grupo de afinidad WIE. Asimismo, un grupo de afinidad de la rama estudiantil y EEE, sección Ecuador, región 9. El día de hoy está con nosotros el doctor Antonio Pascal, quien nos va a dar su conferencia acerca de exploración marítima en cooperativo con robots marinos, ¿no?
Sí,
Doctor, ¿cómo se encuentra?
¿Puedo empezar?
No, eso es lo que le iba a decir. Primero, lo que vamos a hacer es, Gema me va a dar nos va a dar una breve presentación acerca de usted, una biografía, su recorrido, vida académica. No demora
Sí,
mucho y luego procede cuando usted esté listo. Y la
sí,
tercera parte, que vendría a ser la sección de preguntas y respuestas que le mencionamos anteriormente. Para las
sí,
personas que se están conectando, pueden escribirnos sus preguntas en el chat donde dice QYA, ¿no?
muy bien, bien.
Bueno, doctor, entonces, no, cierto, Gema, por favor.
Sí, entonces ok. ¿Tengo que esperar por la presentación? No.
Sí.
Sí.
Ok, muy bien.
Hi everyone, this is our fourth day here. I hope you are enjoying so far all the conferences. We today have Dr. Pascal. I'm going to give a little biography of him. Well, Dr. Pascal is a PhD, he has a PhD in control science from the University of Minnesota, USA. He's a professor of control and robotics at IST, University of Lisbon, Portugal. He's a member scientific council of the Institute for Systems and Robotics. He's the founder and Dynamical System and Ocean Robotics Lab of ISR. He is a coordinator in the thematic area Technologies for the Ocean Exploration and Exploitation of the Associate Laboratory of Robotics and Engineering Systems. He's an adjunct scientist, National Institute of Oceanography. He has expertise in dynamical system theory, marine robotics, navigation, guidance, and control of autonomous vehicles, and network controls and estimation with applications to air and underwater robots. His long-term goal is to contribute to the development of advanced robotic systems for ocean resources, exploration, and exploitation. He has coordinated and participated in a large number of international projects that have led to the design, development, and field testing of single and multiple autonomous marine and air vehicles and systems in cooperation with partners in India, in Korea, in Europe. Well, I think that's all. Whenever you feel ready, Dr. Pascal, you can start. And thank you again for being here with us
Okay.
today.
Yeah, good evening. It's 10 o'clock here in Portugal. Thank you very much for the invitation. Muchísimas gracias por la invitación. Es un enorme placer estar hablando con la gente de Ecuador y otras personas. Bueno, entonces voy a hacer la presentación en inglés. Tengo muchísimos slides para mostrar porque, sorry, English, because the topic is very exciting, but I'll be a bit fast. So to give you an idea, I'm with the School of Engineering of the University of Lisbon in Portugal, and this is the campus, 2 places, and we have a large number of students, and we have very strong doctoral programs with MIT, CMU, and the PFL. So the work that I'm going to talk to you or mention to you is the work of many. So here you see a group of people that work with me. So they keep shifting. And I wanted to start with some slides to convey to you the general idea that much of the work that we do is with funding from Europe, from European projects. And this is fantastic because we have these large groups of people coming from all over Europe. And these are the final tests of a big project in Lisbon. So you can see many people, a couple of vehicles. So we have to get together and learn how to work with each other. So that's cooperation itself. Another project that I will mention, it's called MORPH, with a large group of people from France, Spain, and Italy, taking place in the Atlantic Sea. And finally, I will also talk about this project called We Must. You see even a larger group of people with many vehicles from Portugal and from Italy, and I'll explain to you what this is for. I like to show this diagram because we are engineers, but we have to interact a lot with scientists. So always keep in mind that engineering systems have to interact with science, industry, and innovation, and define and carry out missions at sea. So what are the scientific challenges, as you know? So to develop the methods, in particular the robots, to study all kinds of phenomena that occur in the ocean, in the water column, and the interfaces with the ocean surface and with the seafloor. So in order to do this, you need robots. They are extremely important. So we need technologies for ocean exploration that include networked, this is the buzzword, networked or cooperative networked air and marine robots, and also robotics systems for the inspection of critical infrastructures like offshore wind and wave energy farms or even fish farms. So to give you an example how we started here in Portugal more than 20 years ago, we were in the business of developing surface robots. This is a surface robot here. So these robots are very nice because you can operate them in very shallow waters where the big vehicles do not go, the big vessels. And the idea here was to develop a vehicle to obtain maps of the seabed. Okay, so how do you do this? Now I have to decrease the noise here, not the noise, the intensity of the signal. So this is the simplest example of a surface vehicle. I'm going to cut this out. Okay, a surface vehicle that is completely autonomous, does navigation using GPS in this case, and then when it starts moving, then you are going to see under the vehicle right there. So now you'll see under the vehicle. So the vehicle is following a certain path. It's doing what we call path following. But now here you see the motors, and there you see in black, these are acoustic echo sounders that send acoustic waves that reflect. And by measuring the time of travel and doing simple computations, if you do a very good maneuver over the seabed, then you can obtain a map of the seabed. And this is what you get with a very simple device in very shallow waters. So it's mapping of the seabed in a very efficient manner. This is an old volcano that we have in the Atlantic. So it was the first application that we had in mind, to develop autonomous surface vehicles in order to draw maps of the seabed. And here you see the top of the crater of the volcano and then the volcano itself. Okay. Then we embarked into something slightly more complicated, and we got into autonomous underwater vehicles. So essentially, now you want to examine the water column and maybe the seabed. I'm going to cut on the south. And this is the first underwater vehicle that we developed. It's called the Infante. And here you see it in operation in the Atlantic and coming back to the surface at the end of the mission. So two types of vehicles, surface vehicle, underwater vehicle. But now the important fact is that we have to go deeper. So we have to penetrate the deep sea. So when we do this, we have to face all these challenges because the pressure is very high, the environment is very corrosive, there's no optical visibility, navigation is very hard because when you are underwater, there's no GPS, and communicating with the vehicle is very hard, and with the best modems in the world, probably cannot exceed more than 32 kilobits per second, okay? So the way I got enthusiastic with the use of cooperative vehicles was because we were looking at the situation where you have an underwater vehicle performing a motion and then a surface vehicle, and you have to communicate. So if you send acoustic waves through the acoustic channel, not only do you have the direct ray, but also all the reflections. That's what we call multipath. Then it's quite confusing. It's very hard for the receiver to find out what the image is or what the message is. However, if you keep them aligned, if you have the surface vehicle on top of the underwater vehicle, then you can transmit in the vertical, you avoid the multipath, and the bandwidth goes up. So this was behind the very first project where we used cooperative motion control, where we had an underwater vehicle, a surface vehicle, and now there's a very interesting problem because suppose this one is the master. So this one, based on the exchange of signals, should ride on top of the other one, so they act in cooperation, and this helps in navigation, also in the transmission of images and data that it can relate back to a ship and to shore. So this was the first time I got involved in cooperative motion control, and here you see an artist's rendition of what was happening, the two of them talking to each other. So this is the key element. You need more than one vehicle operating at sea and doing these types of fantastic things. So things evolved a lot, and then starting in about 2009, there were many game changers like small embedded processors, advanced sensor suites, new optical modems, and advanced algorithms for cooperative motion, navigation, and control. Now, I like to see this image because for those of you that are involved or wish to be involved in the use of multiple vehicles underwater, this is a fantastic unit. We did not buy this unit ourselves. It is purchased from Evologics, Germany, but it has all the ingredients that are needed to do cooperative mission control, because here you have a modem. So this is an acoustic system with a transducer, piezoelectric transducer, and when you excite it, it sends acoustic waves into the ocean and someone can listen. At the same time, if you are one vehicle and you want to talk to another vehicle, you can interrogate, receive the answer, and find the distance. And also, when the acoustic wave comes back, it hits these receivers with different phases, and by manipulating, you can find the relative position. So this is a unit that can measure ranges, that can communicate, and can measure the relative position between one vehicle and the other one. Of course, it's a very expensive unit, but it's quite useful for these purposes. So the first time we used this in oceanography, but mostly having to do with biological studies, was in the course of the MORPH project, where the objective was to study whatever happens on the cliffs, on the vertical walls that are near shore. So the biologists tell us that very interesting things happen here. So the idea, how can you send vehicles to examine these areas and take photographs and then do mosaics, do maps of these areas to study the biology? So the engineering solution is here. It was quite interesting at the time because we had 1, 2, 3, 4, 5 vehicles in the water. This one is the leader, knows what it is doing because it has GPS. Then there are 2 vehicles in the water column that are very sophisticated in terms of communications with the leader and also finding their positions with respect to the leader. So they know where they are in inertial space. They are called the anchors. And then you have 2, 3, or 4 more vehicles here that just by measuring ranges to these, they find out where they are. So the idea is to have this group of vehicles start scanning the sea bottom. See, they go like this, they take images and everything. And when they detect a wall, they start going up, talking to each other. And then when you go further up, these vehicles will have to go along the wall and do the mapping. And this vehicle steps back in order to talk to that one. Now, this was very exciting at the time because I think it was the first time that we had so many vehicles in the water. We had 1, 2, 3, 4, 5. And here you see all the ingredients of cooperative navigation and control. They have to talk to each other. They have to help each other to fly information and to react to events. So for this particular project called MORPH, we had vehicles from Spain, from France, from Portugal, from Germany, and from Italy. This gives you an example of a series of pictures that were taken along a wall, and then we performed what we call a video mosaic. So here is an example of the group of people that are doing all this stuff. And then we went in these Azores, and I hope I shall be able to show you a little bit of this. So this is the place where we carried out the tests. And remember, this was in 2014, so it was quite some time ago. This is in the island of the Azores, in the middle of the Atlantic. So now you'll see the support ships here, right there. And then you'll start seeing the different vehicles that participated in the mission. Okay, so there's a German vehicle called SeaCat. There were 2 vehicles from the University of Girona in Spain, and our vehicles Medusa. So the idea was to perform a mission where the vehicles would fly, and then 2 of the vehicles that were closer to the seabed were taking images to do a later analysis of what was down there. So only the top vehicle knows what it is doing. The other ones have to find out and adjust on the fly. So I'm trying to jump. I hope this will work. So all this is done automatically. So you see underwater, here is the unit I mentioned to you. They are talking to each other. And here you see very well the 2 vehicles that are close to the sea bottom, and they are taking images of the seabed and so on and so forth. So it's a very exciting mission because everything has to work to perfection. They have to talk to each other. They have to understand what the leader is doing, so on and so forth. So right here, you have a very interesting application of cooperative vehicles where you have surface and underwater vehicles to do the job. Okay, so now to make it all happen, we developed our own vehicles, the surface vehicles, the underwater vehicles, and we also operate with air vehicles, but that's not important at this point. Another example of a project where we used cooperative vehicles is very interesting because it has to do with the exploration of resources under the sea. So a typical case is you have the seafloor, you have the hydrocarbon deposits, and typically you do the survey to try to find out what is there using a big ship. This ship has what we call an acoustic source that sends acoustic waves that reflect off the sea bottom. They penetrate and they refract, they penetrate, blah, 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 blah. And then the sound gets back to this array of hydrophones that is towed by the big ship. And then by analyzing the data that are acquired, so you see, this is a big commercial operation. It's very, very expensive. So, for example, if you do these things called seismic surveys, sometimes the price goes up to $500,000 per kilometer square. Why is it so expensive? Because you have a big boat that is extremely expensive. Then you have these things with the cables called the streamers that are very long. Sometimes they can get entangled, so it's very hard to deal with all this stuff. It's very interesting because after geophysicists process the data, they can look at the data and they find out what there is there. Now, of course, I don't know how to understand this, but I'm going to show you this beautiful video produced by one company in Portugal. What you are seeing here is amazing. Is with this technique, you are actually cutting different planes under the bottom of the sea. And you can see all the details. So for the oil companies, it's very important to understand because the geophysicists will let them know if there is anything interesting there or not. Now, of course, you can also apply this to the exploration of mineral deposits and other kinds of things that are extremely exciting, okay? This technique can also be used when for example, people want to build farms, offshore wave and energy farms, and they need to lay the foundations and they need to understand what is underneath the seafloor. They can use this technique. Okay, so then we introduced the we must concept where instead of a big vessel that is very costly, we replace this by 2 surface robots. And instead of having these hydrophones or streamers towed by a big vessel, we have autonomous vehicles pulling smaller streamers. So they are totally decoupled from that acoustic source, and you can even dive them to increase the resolution. This was the key element. So I'm going to show you a little bit of the We Must project. I have to go to 242. 240.
Changing the formation of the robots makes it possible to change the shape of the acoustic antenna. This is very important because in this way, the amount and quality of data extracted from the acoustic signals is potentially higher. Furthermore, the lack of physical ties between the surface vessel and the acquisition equipment may greatly facilitate operations at sea.
Okay, so that's the idea. So it's very interesting because you have to develop a bunch of vehicles. They have to talk to each other. They have to pull now these streamers. These streamers are simple tubes that have hydrophones inside and they are filled with oil, you see? So one of the first things that we had to do was to try the cooperative behavior. So I'm going to jump this. So here you see an example where you have 2 vehicles at the surface communicating with each other and pulling the streamers. Now, this is at the surface, so doing the cooperation is easy because you can do Wi-Fi. Things get more complicated if they are underwater, and that's what we did in the scope of this project, okay? So the first thing that we did was to develop an autonomous surface vehicle. It looks very ugly, but it's quite effective, which is a catamaran with electric generators and then capable of generating the acoustic waves. This is done using what we call a sparker. So a sparker has many electrodes. You inject instantaneous power of about 2 kilowatt over a few microseconds. So the water evaporates, and when it comes back to liquid form, it generates the sound, boom, okay? And here is our small catamaran equipped with a sparker that you see down there. All right. And then we use at the same time a vehicle carrying Sparker from Italy. There you go. So this is the first time that we went to see and tried some of the algorithms. So right now you have 1, 2, 3 vehicles, 3, 4, 5, 6, 7. These two are at the surface with the sparkers, with the acoustic sound. These will be underwater pulling the streamers, and this is an auxiliary vehicle. So when you think of this, you have to think of cooperation. They have to cooperate to do the mission. And that's where the beauty of it comes, because now you have to use all the theoretical mumbo jumbo that is available or that you develop. So the keywords are cooperative, motion planning, navigation, and control. So you have to borrow from all of these different areas. So in order to make things work, you need to get into cooperative motion control, where you start by planning the trajectories or paths for the vehicles. Then they have to help each other doing navigation to find out where they are. And you know where they should be, you know where they are, and now you do what we call cooperative motion planning, which is a brand new area of research using network systems, consensus, and all kinds of things. Now, it's very interesting because the same areas have been tackled before in the context of autonomous air vehicles. So that's where I learned much of this stuff with some colleagues from the US, and we published this book on cooperative control of autonomous air vehicles. Now, in this particular case, the thing gets a bit more complicated because you have the two vehicles at the surface. This is the diagram. This is reality as seen by a quadrotor. So they communicate with each other, and then they have to communicate acoustically with the vehicles that are down there. So everything has to be working to perfection. The middleware, in order to make all these vehicles from different vendors talk to each other, is extremely important, but we managed to do this. I'm not getting into the technical details, but in order to make all these things work, you have a vehicle fleet. They have to communicate with each other. And then at each vehicle, you have to have the inner loops that accept commands for speed, heading, and depth. And then here is the middle layer that executes the cooperative stuff, navigation and control. So I'm not going to get into the technical details. Here is a simple example of cooperative motion control that is very easy to understand because this was at the beginning and the vehicles are at the surface. Okay, in this case, it's still relatively simple because all we wanted was for the vehicles to be in line. Only one of them is, let's call it a leader, and the others have to find out where they are with respect to the leader and synchronize the motion so that they are always in line. It's beautiful to see once it starts happening because they go on turns, they do all that. They fight the waves, they fight the currents. So here they go in nice coordination. Now the problem gets a little bit more complicated when you go underwater, but it's possible to do it. Now, full system implementation for the IMAS project. I wanted to show you this video because you see the sparker there. That's what emits the sound. And that's the other sparker. Okay. Now, system implementation, we went in the water to perform all this stuff. Let me go to 107.
The autonomous underwater vehicles, AUVs, and all the seismic acquisition gear was loaded onto 2 boats. The catamarans were towed to the survey site by the same boats. After about an hour of navigation from the Sines port, the survey area was reached. The survey lasted over 2 hours, and it consisted of a mission with 7 autonomous vehicles. 2 autonomous catamarans carrying the Sparker seismic sources, 1 Medusa robot on the surface aiding the underwater navigation as anchor node, and 4 AUVs, 2 Folaga and 2 Medusa robots, towing streamers at a depth between 2 to 8 meters below the sea. The survey consisted of performing roughly 7 laps of a racetrack path.
This is real data.
Of approximately
this
100
is
meters by 200
taken
meters.
by a quadrotor, where you could see all the vehicles doing the mission and then the data that were acquired. Now,
employed to collect seismic data
this was truly exciting because the number of vehicles, 7 vehicles, and doing all these things, to me, it was amazing. It was beautiful to do the, and this is the consortium that was involved. Okay, I don't know if I'll be able to play this. This is very interesting because it shows you the vehicles going to their racetracks. This is the simulation that we did in MATLAB before doing it. And then reality is truly very much like the simulation. Here you see the Sparker, here you see the auxiliary. These vehicles are submerged. And it's beautiful to see this in operation when it happens well. There you go, on the racetracks. So in order to do this, you need to understand about network motion planning, navigation, control, communications, computers, you know, everything. That's why it makes it so fabulous and so exciting. So cooperative navigation, planning, and controls. All right, so these are the types of things. Now, it's very interesting because you can do other exciting things with this. Now, one company in Portugal and another company in Holland asked us, can we do a smaller system, self-contained, to do the seismic surveys in shallow waters? And we said yes. So we just finished a survey for the electricity of France near a nuclear station, central power station, or power nuclear central, in order to find out how the bottom of the sea was and underneath the sea. So we use this beautiful device that is essentially a catamaran with a sparker, and then here you see the floaters and you have the hydrophones here. So for applications in coastal waters, this is a beautiful example of what you can do with a surface vehicle equipped with hydrophones and doing a seismic survey. Now, there are other kinds of vehicles that we have been involved in. I have to go very quickly now. One of them is this Fusion that was developed by a company in the US called Strategic Robotic Systems. And we developed a navigation guidance and control for this beautiful vehicle that can work in ROV mode, in AUV mode, and also as a buddy of a diver. That was very interesting to develop all this. And then we have also been working on deep sea going vessels like this ROV, the Luso. It's a Portuguese ROV that can go to 66,000 meters of depth. It's already a big beast, so it's harder to deal with it. But for studies of oceanography and to study the sea bottom, it's quite fascinating. Now, the interesting here is to use the units on board the ROV to find the position. And for those of you that are acquainted, this is done by using an ultra-short baseline and other kinds of things. This is the operation of the vehicle. And this is an animation of our navigation system working, where you get some position fixes with ultra-short baseline, and you keep estimating using other kinds of sensors. All right. So the big push forward. Now, in order to move forward, it's really important to take big challenges. So I always advise my students not to focus only on the engineering aspects, but think big. Applications in aquaculture, renewable energy, fisheries, so on and so forth, and especially go to the deep sea. So I'll give you a few examples of things that can be done in the future. And these are all projects that we have submitted. One of them has to do with sustained presence at sea. So if you have wind farms, instead of having the vehicles dive and having a surface vehicle following what it is doing, you should leave the vehicles there. That's what we call sustained presence at sea. And now and then they wake up and they do some analysis, they come to the surface, transmit data, and come back. The other project, and this is very important for oceanography, is a project where we teamed up with the Massachusetts MIT. We don't know if it has been approved or not. And the idea is to lay the foundations for an observatory in the Atlantic where we use the space, air, and marine segment to study oceanfront dynamics. So some of you will know what oceanfront dynamics are. They are very rich. And so based on satellite, you sort of predict where they will occur. Now then based on aerial information, you zoom in, and then you send the robots at the surface and underwater to measure what is down there. It's a beautiful application of cooperative networked vehicles in oceanography. And if it is approved, it's truly a showcase of technology assets for science and industry in Portugal, because most of these things are manufactured here in Portugal. The other beautiful project that we submitted, maybe it's not so interesting to you, it's to do what you call karstic exploration, which is to study the extent of the water reservoirs in limestone. It's a very difficult operation because you have to send robots through these tubes and navigate and find out where they are. That's another example. So there you are. It's a very challenging problem, very difficult. And then we also submitted this very interesting one, some of you may be interested, for the detection, this should be tracking and mapping of microplastics in the ocean. So the idea is to have groups of vehicles at the surface and underwater. They carry these streamers and acoustic emissions. And by doing something equivalent to acoustic tomography, they should be able to find out if within this area there are accumulations of microplastics. So this is the problem or the project that we submitted. Cooperation of surface vehicles, underwater vehicles with antennas, acoustic antennas, to try to find out from the acoustic signatures if there are concentrations of microplastics there. And then we also submitted another one for the extension of a WEMAST. I'll spare you the details, but it's quite complete because now we have to use not only acoustic sources, but the streamers, but also magnetic devices and so on and so forth. So when you think of cooperative vehicles or cooperative or networked vehicles, the applications are manifold and they are increasingly important. There's a beauty in all of this because the theory is a bit complicated. Okay, so you have to go through network systems theory, but when it comes to implementing the systems, also you have to go through distributed computer, network communication, so on and so forth. And I have not talked about, some of you may be interested in knowing that there are beautiful applications on the interaction between robots and humans. This is an example of a project in which I participated called CADI that involved the participation or cooperation between humans and robots. So all this has been made possible through the cooperation with many, many, many institutions. And by talking to all of these people, we learn so much. I mean, especially people in the US, in France, in Germany. We are very fond of our cooperation with India, with Norway, and so on and so forth. So it's really teamwork. You need big teams in order to tackle all of these problems. Now, it's very important also to keep an eye on publications because, and I want to mention this because when you work on cooperative systems, then you have to go deep in the theory, so then you can come up with some nice publications, but they are not in a vacuum. Then you can apply this stuff to exciting things. So I think I should stop here now, okay? All right. So I'm open to questions. Hello?
Thank you so much,
Hello.
Dr. Pascal.
Yeah.
We're reading we're about to read questions now.
How can I read the questions?
I'm gonna read you the questions and then you can answer the question.
Okay, that's it.
Let's see. It is possible to use ROV vehicles some project to remove the trash island forming in the Pacific, and how many of those vehicles will need to deploy?
Sorry, to do what? What do you want to do with the ROVs?
Excuse me?
Yeah. Please go ahead.
No sé si mi micrófono me está fallando.
Aquí estoy escuchando muy bien, pero no ha comprendido cuál es la misión a ejecutar con los ROVs.
Hablaba sobre que la pregunta habla sobre si es posible usar estos vehículos para remover esas islas de basuras formándose en el Pacífico y cuántos más o menos se necesitan desplegar.
Muy bien, muy bien, muy bien. Okay, if the litter, okay, so when we talk about microplastics, it's a bit different because you don't see it very well. So in this case, you need sophisticated devices. Now, if you have these concentrations at the surface of the sea, I think it's very interesting to look at the chance of having aerial drones that find out where these things are, and then they work in cooperation with the vehicles that can be robotic vehicles at the surface, but they have to be specially designed in order to collect the litter. But I think it's a beautiful application for all these techniques, yes. ¿Cuál es la pregunta siguiente?
Thanks a lot. The next question, it says, greetings, Antonio. Thank you for your excellent presentation. Have you applied the function of these marine robots in measuring or producing tidal energy?
Okay. So I do not work in that area, but I have some friends that work on renewable energies, wind, waves, and tidal energy, right? So there are many aspects involved. First of all, when you want to install these big infrastructures, you need to find out if the bottom is solid and sufficiently good to install the infrastructures. And that's where you need what I showed you to penetrate under the seabed and to make sure it is okay. Then, when you have all these farms, we can think of farms, right, to capture the energy, then you have to install them on these big pillars. And now and then you need to inspect them. And in order to inspect them periodically to make sure that everything is okay, the best way is to send vehicles that go underwater and navigate around and inspect the infrastructures. So again, you inspect the infrastructures using autonomous robots. These are the two applications that I see of the robots. Yeah?
Yeah, it's okay. Thank you. The next question is from Angelica Bustos. She says, the understanding between the group of vehicles involved machine learning. If that's correct, what happened with the group of if for any reason the leader breaks?
The leader breaks?
Mm-hmm. The leader
Okay.
breaks.
First of all, I talked about the leader, but we don't use the concept of a leader. So remember that when you talked about connected vehicles or connected networks, you have centralized solutions. That's where you have a leader that talks to all of them. That's not good, because if the leader breaks down, that's it. Then you have decentralized, that we don't use either, because decentralized, that's when you give a task to each of the robot, you do this, you do that, but you don't talk to each other. Now, we always go for distributed strategies, where one vehicle is supposed to talk with some of the vehicles in the neighborhood. And we have to show that by doing this, overall, the thing behaves well, even if some of the vehicles fail. Okay, so we always go for distributed approaches to implementation. It requires certain theory, so on and so forth. Now, when it comes to machine learning, to tell you the truth, I'm not excited about using machine learning for motion control and navigation, but I'm excited about using machine learning for other things. For example, suppose you have a bunch of biologists that want to study a certain area, and they want to find out what kind of fish are there, and how many are there, and what is the distribution according to species. So it would be nice to send some underwater robots capturing images and then having some networks trained to recognize the different types of fishes. And then this can be extremely helpful for biologists and ecologists to find out the characteristic of these habitats. So it's very important to use machine learning techniques in these circumstances, okay? All right.
All right, thank you very much for your answer. La siguiente pregunta me están haciendo acá, me dice, ¿qué equipo se necesita para desarrollar un vehículo o un robot submarino? Pero se refiere a un equipo básico, es decir, profesionales, personal. No, es que yo la estaba entendiendo que era equipo de mecanismo y eso, pero me especificó.
Estamos hablando de personas, ¿no?
Ajá.
Ok. Bueno, es una cuestión muy importante porque, ¿cómo explicar? No es posible hacer el desarrollo de estos vehículos solamente con estudiantes, porque es trabajo muy intensivo y tienes que tener ingenieros con experiencia. Y por veces es muy difícil de contratar ingenieros, no sé cuál es la situación en Ecuador, en otros países. Aquí tenemos esta oportunidad porque tenemos proyectos europeos. Entonces, nuestro equipo consiste de estudiantes de mestrado, de doctorado, postdoctorado, y después tenemos siempre un buen ingeniero mecánico, un buen ingeniero de electrónica y un otro ingeniero de sistemas. Mas es posible de empezar de otra manera. Tienen que organizar todo muy bien. Mas mira, es preciso saber un poco de mecánica, de electrónica, comunicaciones. Yo diría que el básico serían unas 6 personas para empezar. ¿Sí?
Excelente respuesta, la verdad, sí. Muchas gracias. La verdad que yo también estaba con esa duda, sinceramente. A ver, dice Luis Escudero, dice, ¿qué frecuencia acústica es la mejor para detectar microplásticos?
No soy el perito en acústica, mas va a depender de la dimensión de los microplásticos, mas tiene que ser una frecuencia elevada. de la orden de mega, porque si no, el comprimento de onda no va a ser comparable de manera ninguna con la dimensión, ¿sí? Mas no sé exactamente. Depende de la dimensión prevista de las partículas de microplásticos. Después tienen otro problema, porque cuando se va a aumentar la frecuencia de la transmisión, entonces la distancia va a ser muy corta, porque las ondas se van a atenuar muy rápidamente. ¿Sí? Si la frecuencia es muy baja, puedes emitir hasta grandes distancias, que puede ser 1 o 2 kilómetros. Mas si la frecuencia es muy baja, el comprimento de onda es muy grande y no va a haber las partículas, ¿sí? Entonces es un equilibrio.
Ya. Muchas gracias por su respuesta, doctor.
Sí, sí.
A ver, estoy a la espera si es que no hay más preguntas. Bueno, al menos
Aún tenemos 8 minutos. Es que alguno de los participantes quiere hacer otra pregunta. Aún tenemos tiempo.
Sí. Una cuestión. ¿Todos los participantes son de América del Sur?
Sí, la mayoría sí.
La mayoría, aunque en otros días sí hemos tenido, por ejemplo, de Estados Unidos. Ayer me parece, unos 2 o 3 que son de habla inglés.
Ok. ¿Y de qué países para del Ecuador? ¿Tiene gente de Colombia, de México, Perú, no?
Sí, el día martes sí tuvimos gente, uno me pareció que era de Colombia.
Ok.
Igual no estoy seguro, pero me parece que sí.
También tuvimos de Perú. Sí, 2 el día martes.
Ok, muy bien.
Aquí también el señor Luis Sena nos está diciendo que él creo que es de Brasil.
De Brasil.
Puso en los comentarios.
Sí, de Brasil.
Sí,
Okay.
también, bueno, debido a que tenemos conferencistas de algunas partes, por ejemplo de Colombia,
Mauricio
de
Perea dice de
México.
Colombia.
Entonces sí se han estado conectando de otras partes también de Sudamérica.
Okay. Mira, tengo una cuestión. ¿Me puedo quedar aquí para asistir a la próxima presentación?
Sí, claro que sí.
Ok.
Me parece que tenemos una pregunta. Solo que...
De Luis Sena también. Dice, specifically related to considering ASB and AUV working connected by cables, the use of inertial sensors can be able to determine AUV position underwater with some help from GPS from the ASB.
Okay, now, as far as I know, nobody's operating AUVs with ASVs connected with cables. Maybe for some simple things, like if you want an ROV with a cable connected to a catamaran in very shallow waters, it would be okay. So now I understand your question, because you are concerned about, for example, if you have a vehicle operating underwater, you need to find out where it is. And it is very costly to develop the system to find the position. But now there are other methods of doing this, and the idea is very simple, and we have experience with this, and it works very well. How can I explain this to you? Suppose that you are in the middle of a town. Let me see here. Yeah, and there is a tower, a church tower, that with the bell, tong, 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 okay? And you are blindfolded, but you know where you are because you have a GPS. if you walk around and keep listening to the sound, and you know what direction it comes from, if you do sufficiently exciting motion, you'll be able to find out where the tower is with respect to you. And that's the same principle. If you have a surface vehicle that maneuvers fast around the underwater vehicle and measures the distance with a very cheap device, then using GPS and the measurements of range, you can find out where the underwater vehicle is. It's very cheap and it's very efficient. Okay?
Muchas gracias por su respuesta.
Sí, sí.
Said thanks.
Okay. Okay, so if there are no further questions, una vez más, muchísimas gracias por la invitación.
Muchísimas gracias a usted.
Okay.
Gracias por habernos compartido de su tiempo para haber presentado.
No es tiempo perdido, es con mucho gusto.
Muchas gracias.
Y más tarde, si tienes necesidad de más información, por favor me contacten, que iré a responder con muchísimo placer. Entonces, me voy a quedar aquí un poquito para asistir un poco a la próxima presentación, ¿sí?
Okay.
Excelente.
Muchas gracias.
Ok, muchísimas gracias. Buenas noches. Okay, now I'm going to book. Okay.
Bueno, nuestro siguiente conferencista es el doctor Milton Kampel. Hi, Dr. Kampel, can you hear me?
Yes, can you hear me?
Yes.
Yeah.
We hear you.
Okay.
So I'm going to introduce Dr. Kampel. Dr. Kampel holds a degree in oceanography from Rio de Janeiro State University, a master's degree in remote sensing from the National Institute for Space Research. He has a PhD in oceanography, biological oceanography, University of Sao Paulo, and a postdoctoral at the Bedford Institute of Oceanography in Canada. He is currently senior researcher at INPE, head of the multi-user monitoring oceans from Space Lab, acting in the coordination of Earth observation. He's a lecturer at the postgraduate program in remote sensing at INPE, responsible for the disciplines of introduction to remote sensing and remote sensing of climate, and an advisor of master's and doctoral students. If you are ready, Dr. Campo, you can start your presentation.
Thank you very much for the invitation, for coming here today. Can you see my screen now?
Yes, we see your screen.
Okay, so let me start with this. I'm changing for presentation screen. Okay, so what brings me here today? Much of the research effort undertaken in the recent years has focused in observation data. Sorry, let me try to minimize this. Okay. So I was saying that much of the research effort undertaken in the last years, they've been focused on the use of Earth observation or remote sensing data associated with development and validation of different remote sensing products focused on ocean applications. The basic idea here is to comment on some activities we've been developing in our Motions Lab at INPE in Brazil, also present some relevant aspects in the field, to see and discuss a little bit about limitations that still exist, and to further expand international partnerships, collaboration and personal training at international level, helping IEEE network stakeholders to stay active, connected, informed, and inspired during this pandemic time. So after this introduction, I will show a few slides trying to explain you who we are, what we do, and then I will go through basic principles of satellite oceanography, which is my main field of expertise, and I will show a few remote sensing applications developed in the Southwest and South Atlantic waters. So I work at the Brazilian National Space Research Institute. Our mission is to develop, operate, and use space systems for the advancement of science, technology, and applications in areas of outer space and Earth's environment, and to offer innovative products and services for the benefit of Brazil and society in general. We follow very much United Nations 2030 Sustainable Development Goals agenda, also subscribe to Paris COP21 2015 agreement, and also the Sendai agreement. You can see on this map here, I don't know if, can you see my mouse, my pointer, or not?
Yes, we see your cursor.
Thank you very much. So we are based in São José dos Campos, São Paulo, in the Southwest and South Atlantic. But we also have different campi around Brazil. We're a staff of around 1,000 people. We have 600 graduate students, plus 10 more postdocs and other fellowships. We are divided in different branches. I work at the Earth Observation branch. I also work in collaboration with Earth System Science and Weather and Climate Center. But there are also areas of space and atmospheric science, space technology and engineering. We have a satellite tracking and control facility, other associated laboratories, and an integration and testing laboratory. Regarding space engineering and technologies, as you are among the engineers here, this branch tries to develop technology and also having an industrial agenda. We have a long time partnership with China, developing Sibers family satellites, and we are also developing 100% Brazilian satellites. They are called Amazonia 1 and 1B, and we've already developed and launched the Brazilian data collection system. Our laboratory integration and testing facilities is quite well equipped, and we've been integrating and testing not only Brazilian missions, but a few other international missions from other countries around in South America mainly. And this is just to show that Sibers, which is China, Brazil, Earth remote sensing satellites, is a family of satellites. We started with Sibers 1, 2, 3, which failed. We had the 2B, the 4. And here you can see a few remote sensing sensors on board Sibers 4 satellites with cameras in the visible and near infrared, and the shortwave infrared, medium wave infrared, and thermal infrared. And a few imagery from Santos Port in the southeast Brazil, in São Paulo, which is the main port of the South America. We have a wide field imagery of 64 meters ground space resolution, a MUX camera with 20 meters resolution, and a panchromatic camera at 5 meters resolution. Those are the ships waiting to go into the port. And December last year, we have successfully launched Sibers 4A, and now you have a WPM sensors, sorry, just cutting here, with 2 meters ground spatial resolution. We still have a wide field imagery, and we still have the MUX camera. And the commissioning just ended in the middle of this 2020. Here we have a few examples of different sensors from WFI, from WPM, here and there, and the MUX camera with 60 meters resolution. We are supposed to have launched the Amazonia 1 last July. Unfortunately, due to the COVID-19 pandemic, we have to postpone, maybe on next December, but still to be confirmed. you have already 60 to 70% ready of the Amazonia 1P, which is similar, is the same bus as the Amazonia 1, but with a different payload. INPE has also been involved in building some CubeSats with universities and other research institutes, and we're planning to build a few other ones. We also have a satellite tracking and control facility. Our main receiving station is in Cuiabá, which is a very central point for South America. And also have a very reasonable launching facility in Alcântara, although Brazil still don't have any rockets. But this base can be shared. We have also a remote sensing data center in Brazil, where we host not only Brazilian missions, but also many other international, which data have been acquired in our receiving stations. We also have another receiving station in Cachoeira Paulista, which is only 100 kilometers from São José dos Campos, where I work. I work at the Earth Observation branch, so it involves scientific and technological knowledge in the fields of remote sensing and geoprocessing, survey of natural resources, and monitoring of the environment. We conduct research, development, and applications in the fields of remote sensing and digital image processing. Here in the left down corner here, you can see a family of tools. They are developed in-house. They are open source and freely available on the internet, starting from a desktop application to a library of codes for geoinformatics applications. TerraView, it's a type of an example of this TerraLib library tool. We also have specific applications for different proposals for data mining, hydrology, deforestation, and decision-making, TerraMA system. We have different programs regarding deforestation monitoring of Amazon and other biomes, the CBERS family of satellites, space and society. And we also work in close collaboration with other regional centers in the northeast of Brazil, in the south of Brazil, and in the Amazonia region. In terms of education and outreach, this could be of interest of the students here. We have a graduate program in remote sensing, providing master and PhD degrees. And we have also short courses in GIS and remote sensing. We have an e-learning program in GIS and remote sensing. We also have annual courses for teachers from elementary schools related to remote sensing technology applied to environmental studies. And we provide online materials such as book, presentation, video classes, both in English and Portuguese, and sometimes in Spanish. Besides the graduate program in remote sensing, Earth Observation branch also supports very much the graduate courses in Earth System Science and Applied Computation. Every 2 years, we organize and host a Brazilian Remote Sensing Symposium with more than 2,000 attendees. And we're supposed to organize the 20th edition of it next year, but we're postponing for 2021. The same for GeoInfo, was supposed to be at the end of this year, and we're postponing for next year. And from time to time, we take part in the Pantanal Geo. Besides remote sensing, there are other graduate courses at INPE, such as in astrophysics, space engineering and technology, geophysics, applied computing, meteorology, and Earth System Science. Most of them provide master's and PhD degrees, but their system science program only provides PhD degrees. And under the Brazilian research funding agencies, there are scholarships for international students. So usually we have students mainly from Latin America taking our course. Myself, have students from Mexico, Argentina, Chile, and Colombia. So INPE has a long history in monitoring systems of land cover, deforestation, and fires in Brazil, started at the end of the 70s and still ongoing today. And it's a huge area to be monitored. And only through satellites we can do that. And you can see some numbers that the Brazilian legal Amazon is bigger than 5 million square kilometers. And you can see which is non-forest is almost 1 million square kilometers. It's a huge area. Although we also have what we call the Blue Amazon. And the blue Amazon has the size of another green Amazon. It's half of the Brazilian continent and is an extension of the continental shelf and an economic exclusive zone as required for the United Nations. And how can you take care of it? As you know, there are global ocean observing systems, tools, integrating different platforms and tools, focus on climate, operational services, human health, and marine ecosystems. And usually you have a lot of tools for direct measurements, such as buoys, ships, gliders, underwater vehicles. They do provide reference points for real-time diagnostics for generating analysis, forecasts and alerts, calibration and validation of remote sensing products. But still, there are many gaps, especially in the Southern Hemisphere. And you can see from this figure here, taken in May 25th of this year. So would such an approach, I mean, installing instrumentation of different types like this on the screen be possible or reasonable? That would be very difficult. So satellite remote sensing is a very reasonable way to go through collecting and interpreting information about the environment and the surface of the Earth from a distance, primarily by sensing radiation that is naturally emitted or reflected by the Earth's surface or from the atmosphere, or by sensing signals transmitted from a device and reflected back to it. I will go back to this later. Examples of remote sensing methods can include aerial photography, radar, satellite imaging, drones, and so on. What are the benefits of satellite oceanography? You can get a synoptic view, which is quite difficult using traditional tools. We can have a very reasonable spatial resolution out a very nice revisit time. We can provide uniform daily, monthly, order time space views and grids with a very good cost-benefit ratio for end users. But there are some limitations. We can get all indirect measurements, not direct measurements. Clouds are a limitation in the visible and infrared regions of the electromagnetic spectrum. And you can only get data from the surface layer, although this could be the most important one for different applications. So we used to say that satellite oceanography or remote sensing tools, they do not replace but complement conventional techniques. We can ask, what are the major challenges to which space program can contribute, oceanographically speaking? So we can provide data and information in oil and gas or in the energy field. We could have provided also for marine spatial planning, for fisheries and aquaculture, weather and climate, natural disasters, a lot of technological innovations and ecosystems monitoring. And you should also mention health and biodiversity. As I mentioned before, you have, United Nations 2030 agenda, and I should mention the GEO, the Group of Earth Observation, which is at ministerial level, and under GEO, you have the Blue Planet Ocean and Society initiatives that I would like to have you notice about. There are other GEO initiatives which some of you could be interested in, such as MBON, which is the Marine Biodiversity Network, AquaWatch, which deals more with inland waters, GeoHealth, Geocarbon, and GeoWetlands, among others. Also, should mention that we are about to start the decade of ocean science for sustainable development. Ocean science is critical in reversing the decline that ocean has slipped into in recent decades, whether it is to address climate change impacts on the ocean, marine pollution, ocean acidification, the loss of marine species and degradation of marine and coastal environments. To achieve sustainable development, good science is needed to inform policies and raise the knowledge of all stakeholders. Nowadays, a key for a buzzword that's very much being spoken is about blue economy. So you should be aware of it. And so what is blue economy? All economic activities related to the ocean, seas, and coasts. Blue economy covers a wide range of interlinking established and emerging sectors. So considering all of this, we have a group, a research group and a laboratory which is called MOTIONS, Monitoring Ocean from Space. So we've been developing applications in different fields such as coral reef studies, mangrove in the coastal zones, algae blooms, climate, water-associated diseases, marine spatial mapping, applications in basin estuaries. We've also been participating in satellite missions developments, inland water applications, ocean color missions, offshore and power generation, fisheries, air-sea interactions, land-ocean interactions, and oil and gas. So let's see a few basic principles. What we see from space. So imagery from satellites allow us to identify and track surface features in the visible, thermal infrared temperatures, but what we can really observe. Mainly, we can have passive sensors using energy from the sun, which interacts with the surface of the Earth or the ocean if we wish, and reflects back through the atmosphere being detected by orbital satellites. And this information is transmitted to receiving stations on the ground. You can also have active sensors, which they have their own source of energy, and so they pulse a signal which interacts with the surface and scattered back to the satellites, and again, this information is transmitted into ground stations. Most of the satellites, they can be usually in two types of orbits, near polar orbits and geosynchronous orbits. And data acquired by satellites are taken in different ranges of wavelengths called bands or channels, and in different wavelengths, as I mentioned, and you can see a coastal zone here, and this is an hyperspectrum sensors, but usually you can have a multispectral sensor. Basically, we use reflected electromagnetic energy and emitted electromagnetic energy that interacts with the targets or the surface of the ocean. Thinking about getting information from a certain distance, we should consider all the process of absorption and scattering in the atmosphere when sunlight goes to the surface of the oceans, sun glints, and other refraction and reflection processes going on at the Earth's interface. Then you have the interaction of this energy of the water column in terms of scattering and absorption. Sorry, this slide is in Portuguese, we don't mention that. And then, depending on the depth and the transparency or clarity of the water column, you can have interactions with the sea bottom. So, remote sensing of aquatic system has potentialities for mapping and monitoring marine ecosystems. There are some complexity for extracting background reflectance information, and you should be aware that atmospheric and water column correction are required. So if you take a look on the electromagnetic spectrum, I should point out that there are some windows and class of sensors usually used by satellite oceanographers. You can divide them roughly in terms of ocean color radiometry, infrared radiometry, microwave radiometry, and active radars. And here you have the atmospheric transmission windows where you can get information above the atmosphere. So there are different classes of sensors. As I mentioned before, we can have passive sensors and active sensors in terms of the source of energy used in the process. You can have visible waveband sensors, infrared sensors, and even passive microwave sensors. Besides the active microwave sensors, they are usually called such as radar instruments. And here we have a lot of engineering, which they develop different instruments to be used as remote sensors in those atmospheric windows. But independent of the type of sensors and in the region of the electromagnetic spectrum you are dealing with, at the end of the day, we have only a few primary observable quantity or parameters. And they can be summarized such as ocean color. sea surface temperature, salinity, surface roughness, and surface slope. We can get ocean color only from visible sensors, but sea surface temperature, for example, we can have from thermo-infrared sensors and also passive microwave sensors. Now, regarding surface roughness, we can get it from microwave sensors, active and passive, and also from visible sensors. And the same for surface slope, and we can get only from active radars. And from those primary parameters, you can have different environmental variables or meteorologographic variables, if you wish, such as chlorophyll concentration, suspended sediments concentration, bathymetry, other optical properties. You can also get sea surface temperature, skin temperature, mixed layer temperature. You can get surface wind, wave height, wave spectra, internal wave, surface slicks, and also geostrophic currents, seafloor bathymetry, ocean geoids, and a few others. But also, you should keep in mind that depending on the process or object of study, there are different spatial and temporal resolutions where you should choose the best type of sensors you can use for your studies. So it's not always that's like a short blanket. It's not always that you can fill or attend both requirements in terms of temporal resolution and spatial resolution. So there is a compromise here. Should keep that in mind. So I show a few examples of passive sensors, such as the one that should, from them you can derive surface chlorophyll, such as MODIS, is a sensor on board NASA, Terra, and Waka satellites. Terra was launched in 2000 and still working up to today. Apple had a problem last month, but now it's back to business. We also have VIRS from NOAA on board Suomi NPP and NOAA 20, which was called before JPSS-1. We have OC, European Sensor on board Sentinel 3A and 3B. For sea surface temperature, you can have MODIS. MODIS do provide dating the visible and thermal infrared. You also still have ADHRR, NOAA, and METOP. We have CVIRI from Meteosat, ABI from GOES-R. You can have microwave sensors such as TMI on TRIM, AMAZAR, WINSAT, AMAZAR2. Now, another basic principles in terms of ocean color, you have the sun, the source of the energy, which interacts with the atmosphere, with the Earth's interface, water column, sea bottom, and then interacts back again until it's detected by an orbital remote sensor. But there are factors that influence the emerging light that leave the water body. So the backscatter by water molecules, backscattering by suspended inorganic material, absorption by dissolved organic matter, the sea bottom reflection, depending on depth and transparency, and backscattering by phytoplankton. If you go to the sea, having a in situ radiometer, this one is an example of an above water radiometer, but you can also have an in water radiometer. And this black line here is the spectral signature of a typical target that you can have from this Earth emerging radiance in the visible and near infrared bands or range, as observed by a satellite above the atmosphere. And here in gray bars, you see the bands of the satellites in a multispectral radiometer. And on B here on the right, is the same target using an imaging spectrometer, which is a different instrument from a radiometer, but with a higher spectral resolution of 5 nanometers. And you can see that you can reproduce much better the spectral signature, the spectral curve of the target. Then you need to rely on algorithms to translate or to transform the radiance, which are measured by the satellites in the visible, into properties that we're interested in. Basically, you have two kinds of algorithms, empirical, and often you can extract only one parameter, such as, for example, chlorophyll concentration, based on band radius or other power loss, for example. equations, and you can have semi-analytical ones, from which you can derive simultaneously chlorophyll concentrations, CDOM absorption coefficients, and also from particulate material. But there are more. There are phytoplankton functional types and be precise also. And basically, you can see you are interested in in-water constituents such as pigments, such as chlorophyll, sediments, and CDOM, and applying empirical algorithms from apparent optical properties such as radiance and reflectance. You can estimate those in-water constituents. And there are also the inherent optical properties such as absorption and scattering coefficients. And for that, you have to rely more on semi-analytic algorithms. And of course, those algorithms, they are developed for global applications, but in many cases, they require local parametrizations for coastal and inland waters. Here I provide you with a list of ocean color sensors, and all this information was get from the IOCCG organizations, and I recommend you to go through this if you wish. And here we have a few examples from a daily coverage from MODIS Aqua satellite. You can see there are still a few gaps which are fully covered in 2 days, and many clouds, and you can see only a few windows of clear water on this. And here we have a derived chlorophyll concentrations in milligrams per cubic meter on a log scale. You can also have aerosol optical depth, cloud optical depth products from the same type of sensor. You have another example from a geostationary satellite with an ocean color radiometer on board. This is Gochi from South Korea. And here you have the attenuation coefficient in 490 nanometers from 5/8 to 2011 in the high sea. With this, you can have an imagery every hour or even less with 500 meters resolutions. And there are a few other similar sensors under development to provide 250 meters resolution on half-an-hour basis. Now moving on to sea surface temperature, you can have the same approach from polar orbiting and geostationary satellites. You can have, as I mentioned before, infrared radiometers or microwave radiometers, both providing sea surface temperature products. And the flow of information here is similar to what you have for other visible products, but this is just showing that you need different expertise in terms of engineering and also physics, maybe, to develop the instruments, the detectors on board the sensors, the transducers, amplifier, digitizers. All these are required for sensor calibration. We have to deal with the physics of scattering and absorption by stratospheric dust, interaction with clouds, absorption by water vapors, and scattering by aerosols, for example. Then you have to deal with surface emissivity effects. To get what we are really measuring here is the radiance from the very micrometer layer of the sea surface, which is called as skin temperature. But many times you have to build skin built models to extract what oceanographers used to call the bulk temperature or fundamental temperature. So here you can see a few different concepts of what we call sea surface temperature. So as I mentioned before, you can have a skin, which is a few micrometers depth temperature. You can have a thermocline with a few meters up to 10 meters with variations during the day and night. This is what an infrared sensor sees, and this is down below what a microwave sensor sees. And most of oceanographers are interested in this foundation temperature. So we have to build such a kind of a model to go from what each sensor can really provide us, what end users are looking for. And the basis, the physical basis for this is all about black body radiation and Planck equation, okay? So temperature is related to emissivity, okay, to emissivity and to emittance or excitance, if you wish, okay? There are some difference in terms of microwave sea surface temperature. I mean, is also based on Planck's law, but they have the advantage of application in cloudy conditions, as clouds are transparent for microwave radiation. However, the use of these techniques for deriving sea surface temperature is subject to other noise or other errors related to variations in wind speed and foam cover on the sea surface. So the resolution, spatial resolution and accuracy of sea surface temperature estimates in the microwave region are relatively lower than the ones we can get in the thermal infrared due to the lower signal strength in this range. And so we will have a signal to noise, a lower signal to noise ratio in the microwave. And for this, it will require a bigger or a higher spatial resolution pixel. For the thermal infrared, you can have a spatial resolutions from 1 or even less to 10 kilometers, while for passive microwave, we will have a spatial resolution from a quarter of 25 to 100 kilometers. The precision by pixel would be from 0.15 to 0.5 degrees Kelvin, and for microwave only up to 0.5 Kelvin. Accuracy for thermal infrared is lower than 0.1 Kelvin, a few tenths, and here is also a few tenths. Limitations in the thermal infrared is cloud coverage, although we don't have this limitation for microwave, but we still have limitations in terms of rain, surface roughness related to wind blowing on the sea surface. Distance from the coast and ice are usually from 20 to 50 kilometers, so we cannot get coastal data from this, and also other radio frequency interference. Temporal resolution by sensor, without considering the clouds, of course, but satellite passages, they can be lower than 1 hour from geostationary satellites. Indeed, GOES 16 satellites can provide every 10 minutes, but usually for polar orbits, you can have 2 times per day on the equator, increasing the number of passages going to higher latitudes. And with microwave, you can have around from polar orbital sensors to twice a day. We have a longer time series in the thermal infrared since the 80s, and passive microwaves only start at the end of the night. We have just an example. Here we have a sea surface temperature derived from ADHRR, which is a polar orbiting satellite in thermal infrared. And down here you have a TMI, a passive microwave sensors. And you can see clouds in white up here. They do not show up down here. And you have a lot of polar orbit emissions with microwave and optical sensor providing sea surface temperatures. Sentinel-3 also have a thermal infrared sensor, TWIM, WINSAT, GCOM, HY from China, Aquaterra, GCOM-C. We have also meteorological missions such as SWAM-MPP and the GPSS with PIRS, METOP with ADHRR and FY from China. You have the geostationary meteorological missions such as Meteosat, second generation, FY, Himawari from Japan, INSAT from India, GOES from US, and COMS. And here I will leave with you a list of sea surface temperature sensors. Those are links. You can go through microwaves and thermal infrared, different ones. And also should mention PODAC from NASA and also the NASA Ocean Color Web, which besides Ocean Color products also provides surface temperature. Moving on to another interesting oceanographic passive sensors are the ones such as the Aquarius SAC-D from CONAI NASA, which has been in operation from 2011 to 2015. And this is a type of international mission tested and integrated in these facilities. The SMOS from ESA, which is still in operation, SMAP from NASA, also still in operation. Here you can have a global picture of sea surface salinity acquired from Aquarius. And here you have another example from SMAP, okay, this from last year. And as some of you maybe know, sea surface temperature and sea surface salinities, those are conservative parameters from water masses, and you can identify water masses globally. And here we have an example of sea surface salinity SMOS global average on the left, and you have a sea surface temperature global in January 2012 as an example. and you can also have density flow calculated from both products. Now moving on to active sensors. So active sensors, as I mentioned before, they emit their own radiation, which in turn is absorbed and or reflected, scattered by the atmosphere, by the continents, and by the ocean. So active sensors, for example, can rely on altimeters and scatterometers. For example, scatterometers such as ASCAT, they are operational now on board METOP A, B, and C from OMETSAT, SCATSAT from India, and some time ago you had from Israel, and some time ago you had Rapid Scat on International Space Station, and Quick Scat, which provided a very interesting long time series. And from that you can derive surface ocean wind vectors, for example, from scatterometers, and from altimeters or radar altimeters you can derive sea surface height, and we have a list of altimeters that I will show later on. JSON2 is not more operation, is to have JSON3. Sentinel-3 also have an altimeter, and soon you have SWOT with a different technology, very interesting. Why altimetry? Because from altimetric data we can define the Earth geoid, study dynamic topography. We can study ocean dynamics, identifying meanders and eddies, fronts, and geostrophic currents. We can monitor sea level trends, and also can provide different products such as wind speed, wave height for marine weather prediction. You can see here in this picture, sorry, I forgot to mention, here is the source, and you can see a few tide gauges with records longer than 40 years. In the Northern Hemisphere, we have much more than in the Southern Hemisphere, you can see here, but there aren't many. But here you see the coverage of high precision altimetry missions in repeated orbits. So in red, I don't know if you could identify from there, but you have JSON in yellow, ENVSAT, and Sarawautica. The colors are a little bit changed here, sorry for that. But you can see easily that comparison is really unfair in terms of spatial coverage. So total height is estimated by the pulse return time, which the satellite transmits to the ground and reflects back to the satellite. The height of the sea surface in relation to the terrestrial geoid is estimated by subtracting the local effects of tides, winds, and currents. And so you should define very precisely the position of the orbit of the satellite at the time of data acquisition. There are a few issues, and I'm going to skip that because we don't have time for this. And just to show again in a glance what are status of altimetric missions in operation now, and the ones which are already approved and proposed, and you can see SWOT is approved and be under development. You have Sentinel-3C and B under development. You have JSON-CS, Sentinel-6A and B. So hopefully you won't have any gap in the future, in the near future. Here you have different sea surface height remote sensing products from different historical satellite sensors such as GEOS-3, CSAT, GeoSat, radar altimeter on board the RS-1 and 2, GFO, the PAX Poseidon, JSON-1, radar altimeter on ENVSAT, JSON-2-3, Sarawautica, Sentinel-3A, 3B, HY, 2B, 2A, 2B, 2C, 2D, and so on. And a good source of altimetry data is from Avizor, but you can also get it from Marine Copernicus and so on. Now moving on to ocean surface wind. Why is it important to take measurements of ocean surface winds? Because it's usable for sea state monitoring, for identifying cold fronts, extratropical cyclone, high pressure centers, and other meteorological transient features. Ocean atmosphere interactions in terms of sea breeze, monsoons, hurricanes, typhoons, and other climatic events such as El Niño, La Niña, swell formations, coastal currents and upwellings, weather forecast models and climate wave forecasts, These data are useful for parameterizations in the calculation of heat, humidity, gas exchange between the atmosphere and the ocean. And winds are responsible for a large part of the transport of heat and salt and a determinant in the climate balance. We have the history of scatterometer development started in CSAT in 1978. It worked only for almost 3 months. And then we've got, so you can derive wind information from both altimeters and scatterometers. From altimeters, you can get only wind speed. From scatterometers, you can get wind and velocity and direction. That's why you call vector. Okay? How to measure? Basically, I will show only one slide. The wind stress on sea surface produce capillary waves by transferring momentum. Capillary waves are on the order of half of radar wavelength, using a view angle higher than 30 degrees, are mainly responsible for the strong return signal, which we call sigma zero, caused by Bragg scattering. So here we have winds, or this is in Portuguese, and this is the relation of radar wavelength and the waves on the surface, and where you can get that the surface waves are related to the wavelength of the radar signal. So here you're supposed to have lambda equal 2.5 centimeters, which is usually referenced as the C band, and around 1 centimeters for PU band radars. Here we have a chart of present and future scatterometers, and now operational ones are ASCAT 1 and 2 and A, B, and C on board METOP European satellites. And also have SCATSat from Israel. And here we have different remote sensing products for wind. Historical ones as ADIOS 1 and 2, Cygnus, Rapid Scat, and Scat, Quick Scat, CSAT, and Wind Aquarius ACD. And you can have like blended products such as cross-calibrated multi-platforms and individual missions products. And the last system, active system I will show you very briefly is synthetic aperture radar, SAR, and it's a very interesting sensors. You can derive a lot of products. I'm not sure if Professor Migliaccio yesterday presented you mentioned about that during this talk, but mostly they've been relying on commercial missions. And with Sentinel-1, A, and B from Copernicus ESA constellation, now since 2015, we can get freely available SAR imagery. And there are different applications you can develop using this type of information. You can derive high resolution wind fields. You can detect oil on sea surface, also detect ships. You can study internal waves. You can derive bathymetry for shallow waters. Also monitor atmospheric systems such as rain cells, fronts, and a few other ones. And you can have some upwelling signatures, bathymetric signatures, more upwelling signatures, and here we have an oil slick. And with all this information together, you can develop different applications in marine and meteorological services, such as monitoring and forecasting weather and climate, sea state monitoring and forecasting, waves and currents. You can monitor natural disasters such as storm surges, coastal erosion and floodings, oil spill monitoring and control, environmental monitoring of parks and marine reserves, for example, or marine protected areas, fisheries and aquaculture, including algae blooms, and also applications in tortugas. And in different coastal and oceanic studies, you can develop applications for climate and anthropogenic change, weather monitoring and forecasting, ocean atmosphere system, fisheries and agriculture, coral reefs, mangroves, oil spill, and natural disasters. If we have time, I can show a few examples, such as operational meteorologicos monitoring along the Brazilian coast. We've been doing this operationally. providing sea surface temperature charts daily, ocean wind vectors, satellite precipitation estimates, ocean color products. We've been calibrating and validating regional algorithms, feature extraction such as frontal currents, eddies, and meandering, and also the association of frontal systems with wind and precipitation derived from remote sensing sensors. We have an example of oil slick monitoring. This is the eastern coast of Brazil. This is Cape Frio in Rio de Janeiro. This is Bahia State. And we also integrate SAR information, synthetic aperture radar, the microwave, with sea surface temperatures and chlorophyll or ocean color products to identify what could be oil, what are not oil, but yes, you know, it's an environmental feature such as an upwelling, a low wind area, or a rain cell, for example. And there are some other features we don't know. So you need to send a ship, an airplane for confirmation. Here we have an example of an oil seal. So using synthetic aperture radar, we can see the signature in dark, so a lower backscatter signal here. And we can also have another SAR image from a different sensor, an ASTER imagery on board the Terra satellites, and a CBERS imagery, Brazilian satellite, plus chlorophyll and sea surface temperature. Here you can see also an oil spill in the coast of Rio de Janeiro state in Brazil, and this is taken from a sun glint image, a moldy sun glint image. The sun glint can provide you a type of data which is very similar to SAR. Okay, here we can see SAR and visible ship discharges. Those are ships, and you can see oil discharge. And you can also observe biogenic surfactant films, such as from algae and other fish schools, oil films of anthropogenic origin, could be effluents or even pollution, fronts and currents, eddies and meanders, and upwelling films. Here we have an example of a huge feature, which is an oil slick alike, but indeed, when going to the sea, you see that is a huge bloom of trichodesmium, which is a cyanobacteria. And here you can see the area of relatively positive anomaly of chlorophyll, negative anomaly of surface temperature, and here you can see the wind, all from satellite imagery. This is an example of integration of numerical modeling with sea surface temperature and ocean color imagery. You can catch the Brazil current and eddies. And here we have also the integration of satellite tracked drifters, or low-cost drifters, and superimposed on surface temperature and ocean color charts. And those are oil and gas exploration fields along the Santos Bay basin in Brazil. You also have an operational sea state wind and waves forecasting system from our weather forecast center. We provide wave height, wind, and other derived informations, and you do operationally comparisons or validation with automatic data and whatever is available. Here we have like an effort taking time series of surface wind vectors. We could build a climatology of winds. We can estimate power and estimate also the potential offshore wind power generation along the Brazilian continental margin. Here we have example of monitoring of river plumes. This is the Doce River plume, and you have a huge accident on a mining dam upriver, and you could monitor the plume of all the oil and the pollutants going to the sea using satellite imagery. We also have been studying the Amazon River plume, which is quite optically complex. It's an ongoing work. Now we have a project dealing with the biogeochemistry blind spots in the lower Amazon River continuum from land to the sea. And we are planning to go to the sea very soon after pandemic. We also, in our group, also took part on the findings of relatively mesophotic corals or reefs that that are speaking along the Brazilian north coast under the Amazon River plume, and you have the opportunity to dive into this submersible. And here is the highest biodiversity spot in the South Atlantic, which is the Abrolhos Bank, along the coast of Bahia State. And we've been doing some field work there, diving, geography, above water radiometry, in water radiometry, and trying to do the bio-optical characterization of the region. We also have been making some efforts on coastal monitoring. And here we have examples of spatial temporal dynamics of mangroves in the northeast of Brazil using medium spatial resolution sensors. Here we have another example in the southeast of Brazil of mangroves mapping and classification using SAR data. And here we have in Rio de Janeiro, also in the southeast, but on another site, using LiDAR for above ground biomass estimations of mangroves. And here I have a few examples of trying to study basin estuary. This is Guanabara Bay, this is Rio de Janeiro City. So you can see what you can get from 300 to 750 meters, 100 meters resolution sensors such as VIRS, infrared, from ADVRR with 1 kilometer resolution. Those are satellite GOES, geostationary GOES precipitation estimates. Those are winds from scatterometers. And this is a SAR image of the Guanabara Bay with the ships waiting to go into the port. We also have a coastal time series, which is called Antares Ubatuba in São Paulo, close to Ilhabela. We've been running this time series for more than 10 years now in collaboration with the Oceanographic Institute of the University of São Paulo. So this site is suitable for calibration and validation of satellite remote sensing products, also for monitoring changes with time. We've been also doing some research efforts in inland waters, and you can see in São Paulo State, the Tietê Cascade system, and other, as you know, I mean, 40 to 50% of the Brazilian energetic matrix is based on hydroelectric power. So there are huge reservoirs all around Brazil, and we've been doing some studies on those in terms of water quality. And as a coincidence or not, just 2 years ago, we started to make some effort to have students and trying to collaborate with international groups in terms of Earth observation applied for water-associated diseases before knowing what is going to happen as this year. So I'd like to thank you very much for your patience, for having me talking for so much time. I will pass the floor for your comments and questions if you wish. Sorry for showing so many slides, but as you know, this is what we've been doing the last 20 years. So thank you very much.
Thank you very much, Milton. Thank you for accepting my invitation to the new Era of Oceanography. Your presentation was enriching for the participant and me. Knowing about remote sensor is very useful for the advancement of research in the oceanography. Thank you. Now we are going to this question and answer session. Tema? Gemma, tienes apagado tu micrófono.
Hi. Thank you, Dr. Kampel, for your presentation. Now I'm going to ask some of the questions that we got. Well, the first question is, what is the allowed limit of cloud cover to be able to work with a satellite image?
Okay, this is an interesting question, and based on my experience, I should say the following. When you are in the field, it could be on a ship or on the coast, and you take a look in the sky and you see many clouds, you think, I cannot get an imagery here. But it's not the case, because sometimes you can see holes or gaps in between clouds, so you still can get useful data, even working with that. Also, depending on the cloud or the type of clouds you have, there are nowadays very powerful atmospheric correction schemes, such as polymer, for example. And so you should not think, because today is cloud, we are not going to take the data, because it changes time to time. Also, if you are using a geostationary satellite, which will provide with hourly imagery or even more than one image per hour, so the clouds, they will be moving. So we can get also gaps into those clouds and get the images. But indeed, when working, for example, in the Amazon region during the austral summer, it's very much cloud over there, and you should try to skip that time or use different type of sensors, not working in the visible, neither in the infrared, but only in the microwave region.
Thank you so much. We have another question. This is from Charles Novoa. It says, hello. Can we see in these products the currents generated by tsunamis?
If you can see what related, if you can...
We can see in these products the currents generated by tsunamis.
Currents, okay. So there are two things here. So the question, I've heard that mentioned currents and tsunamis, okay? So tsunamis, so you can, as you know, is a very long wave, but with a very small height in the open ocean. Yeah? And so, but still with doing a lot of filtering, you can search for it. But of course, I mean, you do much better work with buoys installed along the coast, as you probably do in the Pacific coast, again. Although we don't have tsunamis here in Brazil. And now talking about currents, is different. Not currents derived from tsunamis. I am not aware of this. Sorry, but I cannot speak very much. But let me take this opportunity to say that we can derive different products in terms of currents. For example, as I mentioned during my presentation, so geostrophic currents from altimetry is an operational product. This is one thing. Also, considering ocean color imagery and even more thermal infrared imagery, we can get from sequential imagery, we can get maximum correlation products, and then you can get surface currents from this, also operational. But we cannot get the 3D structure. So I took the opportunity to mention something about currents, but I cannot say very much about the tsunami, currents associated with tsunami. Sorry.
Thank you, Dr. Kampel. We have the last question. It says, can we obtain that nutrients data by remotely?
I think I understand. Yeah. So unfortunately, my answer would be no and maybe yes. What I want to say is that, for example, differently from salinity, temperature, and those other ocean color sensors from which you can get a spectral signature of it is the signal that we are usually detecting from satellites. Nutrients still don't have a direct signature on these spectral features. However, let me take the open ocean or, you know, Galapagos region, or even the equatorial Pacific regions where you have huge divergence and then you have upwelling, or more to the north, in Costa Rica, you have the Papagayo Straits. So you have areas of higher productivity all along, mostly all along the Pacific coast of South America. So you have upwelling. When you have the upwelling, Then you have colder waters coming to the surface. So you can have a very reasonable correlation of higher chlorophyll, lower temperature with nutrients. So you should think about building empirical models to indirectly estimate this type of nutrients, such as, for example, nitrates, because this type of productivity, I mean, mentioning briefly, it will be enhanced by new nutrients, nitrates mainly, coming from subsurface waters into the surface, associated with colder and more richer waters in terms of chlorophyll. So you can build type of empirical algorithms, and they will work in certain regions, but they won't be global algorithms. So that would be my short answer for this.
Thank you so much, Dr. Kampel. I think this presentation, it's been really interesting, and I think it has helped us. Well, I think we can communicate with you if there are more questions. Thank you for your time. Thank you for being here, and thank you for your participation.
Thank you again for the invitation. If you wish, you can send me the Q&A questions by email, and I will try to answer them. Thank you very much, and hope you have a productive end of the day. Bye-bye.
Thank you. Bye.
Thank you. Bye. Okay. Now, bueno, nuestro siguiente ponente es el ingeniero Hugo Rico, con el tema Identificación de patrones meteorológicos de la convección profunda mediante métodos de observación. Ingeniero Hugo Rico.
Hola, buenas tardes. Buenas tardes, ¿cómo están?
Mucho gusto. Voy a presentarlo y luego podrá compartir sus diapositivas.
Vale.
El ingeniero Hugo Rico es graduado en la Universidad de Francisco de Paula Santander. Es máster en meteorología en la Universidad Nacional de Colombia. Es director y fundador del Centro de Investigación Aplicada en Hidrometeorología, con experiencia en meteorología y de cambio climático. Ha trabajado en el diseño e implementación de sistemas de alerta temprana, como por ejemplo en el Golfo Morrosquillo, en Colombia. Es dependiente del Ministerio de Medio Ambiente y Desarrollo Sostenible. Bienvenido, Hugo Rico.
Bueno, muchas gracias de antemano por la invitación. Estoy muy complacido de estar acá y pues voy a empezar a compartir mis diapositivas. Ya, creo que ya la están viendo, ¿cierto?
Sí, ya la vemos.
Ok. Bueno, el título de esta presentación es Identificación de patrones meteorológicos en la convección profunda. Es un trabajo que venimos desarrollando desde la Universidad Nacional de Colombia en Bogotá. Y digamos es de mucho interés pues por el posicionamiento que tenemos en el planeta. Estamos en el trópico donde hay digamos unas tasas de radiación muy altas y nos da, digamos, para estudiar este tipo de fenómenos que son muy importantes para el planeta por la importancia que tiene el fenómeno como un mecanismo de enfriamiento del planeta. Entonces, pues el contenido que tenemos para la tarde de hoy es, digamos, aprovechando, digamos, este espacio y la invitación que se hizo a través del Instituto Javeriano del Agua, queremos mostrar un poquito de lo que hace el Instituto Javeriano del Agua. Y en convenio, como venimos trabajando con el Instituto Javeriano del Agua, está el Centro de Investigación Aplicada en Hidrometeorología, del cual, pues, digamos, yo soy fundador y estoy a cargo de la dirección del Centro de Investigación. Y pues trabajamos muy de la mano con el Instituto Javeriano del Agua en Colombia. Aquí ya empezamos Debemos abordar el tema de la convección profunda, el vapor de agua, y digamos ya el tema de cómo se hace la observación con satélites, con una red de sensores basados en sistemas de posicionamiento global y algunos resultados preliminares de las aplicaciones. Entonces, digamos ya para abordar el tema, el Instituto Javeriano del Agua es una unidad académica de la Pontificia Universidad Javeriana y une 3 facultades como la Facultad de Ciencias, Ingeniería y la Facultad de Ciencias Ambientales y Rurales. Este instituto pues, no tiene mucho tiempo de estar creado, tiene cerca de 3 años de estar creado y nace por la necesidad que tiene digamos, el país de poder abordar los temas del agua de una forma integral. Tienen unas líneas de investigación basadas en la gestión del recurso hídrico y sistemas socioecológicos, un tema que está, digamos, muy de moda y el país, nuestro país, Colombia, ha empezado a abordar es el tema de seguridad hídrica. Tiene otra línea que es el recurso hídrico, ecosistemas y biodiversidad, y el tema de aprovechamiento, conservación del recurso e infraestructura sostenible del agua. Que, digamos, este instituto, como les venía diciendo, lo que quiere es aportar un conocimiento integrando, digamos, esas 3 facultades, pero muchos, digamos, aporta mucho más que esas 3 facultades. Entonces tiene un conocimiento interdisciplinario. La idea es que pueda dar soluciones integrales para las necesidades que tiene el país y los sectores del país en el tema del agua. Digamos, el agua como un integrador de sociedad. Y el Instituto Javeriano del Agua, pues, tiene como 3 líneas para una propuesta de valor, que es la consultoría. Hacen consultoría con las empresas del Estado o con otras instituciones. La divulgación del conocimiento y la investigación básica y aplicada. Digamos, desde este instituto están digamos, otros programas académicos de la Pontificia Universidad Javeriana, como es la maestría en hidrosistemas y el doctorado de ingeniería, donde, digamos, se integran estudiantes de estos programas en los proyectos elaborados por el Instituto Javeriano del Agua. Y ya el Centro de Investigación Aplicada en Hidrometeorología, pues nació como por la necesidad de tener un instituto que pudiera integrar las empresas del sector privado, del sector público, con la academia. Digamos, aquí la academia muchas veces está como un poquito aparte de los problemas que afronta el país, y pues de este modo se quiso crear ese instituto para poder integrar, digamos, estos problemas y poder dar solución de una forma integral, igual que el Instituto Javeriano del Agua. Y con el Instituto Javeriano del Agua venimos trabajando, digamos, en convenio. Como parte, digamos, nosotros trabajamos más el tema de meteorología y pues eso está muy acoplado a las soluciones que da el instituto. Y el propósito, pues, como yo les venía diciendo, es poder responder a esas necesidades, pero bajo el sistema de ciencia, tecnología e innovación. Aquí en Colombia, desde este año, básicamente, se creó el Ministerio de Ciencias y pues hay una línea muy clara de ciencia, de tecnología e innovación, donde las universidades y los institutos dan respuesta a los proyectos que tienen los territorios. Entonces, la idea con el Instituto Javeriano del Agua es poder trabajar en esas propuestas y darle un valor para las soluciones a los territorios. Y en este momento estamos en el proceso de ser reconocidos por el Sistema de Ciencia y Tecnología del Ministerio de Ciencias acá en Colombia, pero también venimos desarrollando una serie de proyectos como pues, asesorías en el diseño e implementación de sistemas de alertas tempranas, como lo decían anteriormente, en el Golfo de Morrosquillo, que es una zona en el Caribe colombiano, donde queda un puerto de carga de petróleo, y allá sale la exportación del petróleo de Colombia. estamos desarrollando y diseñando una plataforma de toma de decisiones para el sector agrícola con el Instituto Javeriano del Agua. Estamos pues, en unos proyectos de hidrometeorología del sistema de ciencia y tecnología de MinCiencias. Estamos aplicando unas convocatorias para unos proyectos en el norte de Colombia. Y estamos también desarrollando capacidades computacionales. Tenemos dentro de nuestro equipo pues, una persona que trabaja con sistemas de cómputo de alto desempeño. Entonces estamos con él desarrollando esas capacidades computacionales porque pues nos hemos dado cuenta que en el país se requiere implementar ese tipo de modelos para poder responder preguntas a partir de modelaciones y ejercicios de modelación en el país. Y también pues el estudio de la convección profunda en zonas como Bogotá, La Mojana y digamos en general lo que respecta al tema de meteorología pues en Colombia. Bueno, pues como se ha nombrado abiertamente en esta presentación, pues habla mucho del tema de convección profunda. Pero, ¿qué es la convección profunda como tal? ¿O qué es la convección como tal? La convección es un proceso, básicamente, desde el punto de vista físico, es un proceso para transferencia de calor. Los otros procesos son la radiación y la conducción, y la convección es otro de los procesos. Básicamente en la atmósfera es uno de los procesos más importantes de los procesos atmosféricos. Son los que permiten digamos, ese ciclo hidrológico para la producción de precipitación y se comienza, digamos, el comienzo de la convección se da por un calentamiento del suelo que hace que haya unas diferencias, unos gradientes de temperatura importantes entre el suelo y la atmósfera y empiece, digamos, esas parcelas o digamos, esos volúmenes de vapor de agua ascender a la atmósfera. Digamos, ahí hay un proceso muy importante porque esas masas de vapor tienen que vencer la gravedad y eso se da mediante el calentamiento de la superficie. Puede ser el agua o puede ser el mismo suelo. Si las condiciones de la atmósfera y del suelo son suficientes como para que la fuerza de flotación, así se llama, sea suficientemente grande, eso va a ascender digamos, a lo que se llama convección profunda, que básicamente es tener unas alturas de convección muy altas, donde se forman unas nubes muy grandes y generan unos fenómenos, digamos, hidrometeorológicos muy fuertes. El tema de precipitaciones muy fuertes que generalmente están acompañadas de actividad eléctrica, cuando esas masas de aire pues suben a unas alturas que pueden llegar incluso hasta los 20 kilómetros, casi al límite de la tropopausa. Ahí se generan ya cristales de hielo y empieza a generarse también actividad eléctrica. Y generalmente la convección profunda es característica de eso, de unas nubes que generalmente son cúmulos o cumulonimbus y que tienen unas alturas grandes, entre 2 kilómetros y 20 kilómetros. Generalmente oscilan alrededor de los 15, hasta los 15 kilómetros y de una extensión horizontal también muy grande. Pueden extenderse a varios kilómetros, pueden cubrir una ciudad. Acá en Colombia, en la ciudad de Bogotá, que es una ciudad que tiene más o menos 9 millones de habitantes y de una extensión de terreno bastante grande, muchas veces se han generado procesos de convección profunda y unas nubes que cubren casi toda la ciudad o un poco más de la ciudad. Entonces, esas son las características de ese tipo de convección profunda. Y pues obviamente esas masas van ascendiendo y se van expandiendo en la medida que van subiendo. Y a veces pues no necesariamente se genera esa convección profunda, se genera una convección que se llama la convección somera, y esa convección somera lo que hace es que sube a cierta altura y la atmósfera no tiene una suficiente inestabilidad como para que se pueda generar esos ascensos a unas alturas más altas. Entonces se genera una convección, lo que se llama una convección somera, y se genera una capa de mezcla. Generalmente esas Estas nubes son muy turbulentas y se simulan con modelos numéricos, pero es muy complejo poder simular una nube de estas. No es fácil poder predecir los sitios donde van a ocurrir, tiene un componente estocástico alto, pero pues digamos, en el planeta se tienen identificados ya los sitios donde más ocurrencia hay de este tipo de nubes. Como les contaba, pues este tipo de nubes tiene unas fuerzas de arrastre muy fuertes, se arrastra por un lado, generalmente precipita por otro lado, y hay una retroalimentación de corrientes en esa nube, y generalmente, por lo grande que son ese tipo de nubes, la duración de esos eventos de precipitación son también incluso de horas. Entonces, pues aquí tenemos varios procesos donde la humedad va por un lado. Generalmente cuando hay ese tipo de eventos de convección profunda, de estas nubes tan grandes, también se producen vendavales también muy grandes, porque hay unas corrientes de aire. Cuando la nube está en las partes más altas y condensa ese vapor de agua que ascendió, libera unos flujos de calor latente, y esos flujos vuelven y descienden, pero descienden a unas velocidades bastante altas. Entonces se generan unos vendavales en la zona donde está precipitando. Entonces esos eventos están acompañados no solamente de precipitaciones fuertes, de actividad eléctrica, granizadas, porque se genera a unas alturas muy altas, y generalmente en esas zonas se congelan esas gotitas de agua, sino también de fuertes vendavales descendentes desde la nube. Entonces, esas son como las características, digamos, de esas nubes de convección profundas. Como les decía, se da generalmente en nubes tipo cumulus o cumulonimbus, así como lo muestro, pues tenemos en esta diapositiva. Entonces, ya para hablar del tema de precipitación, pues podemos ver este mapa de Colombia, donde se ve la distribución de la precipitación anual, multianual, en el país. Este es del Atlas Climatológico del IDEAM. El IDEAM es el Instituto de Hidrología y Meteorología y Estudios Ambientales. Eso es lo que quiere decir IDEAM, y es el instituto que se encarga del tema de meteorología en Colombia. Lo que nos muestra este mapa es que en nuestro país la precipitación tiene una alta variabilidad espacial, y pues eso se da por la alta complejidad del terreno que tiene nuestro país. Pues tenemos unas cordilleras que atraviesan el país, se desprenden 3 brazos, los colores más hacia azules y, digamos, magenta, son donde más precipitaciones se da. Entonces tenemos una de las zonas donde más precipitaciones se da incluso en el planeta, que es la zona del Pacífico colombiano. Obviamente esto está influenciado por una serie de fenómenos meteorológicos como el chorro del Chocó o la enclave de Panamá. Tenemos precipitaciones muy variadas, digamos, en el valle del río Magdalena. El río Magdalena es el río más grande y más importante del país. Nace en el suroccidente de Colombia y recorre casi todo el país para desembocar en el río Magdalena. Entonces, pues este río, pues esto que estoy señalando acá es lo que se llama el Valle del Magdalena, y es una zona que es un cañón básicamente, y por ahí también se encausan los vientos que transportan humedad en el país, y esa humedad, dependiendo de la época del año, se distribuye o desde el Mar Caribe por el fenómeno de brisa marina, o si no, desde la Amazonía. Los vientos transportan este vapor y empieza, digamos, en ciertas zonas, por el efecto de la montaña, a precipitar. Entonces tenemos la zona del Magdalena Medio, que también es una zona de altas precipitaciones. La zona andina, pues, que no tiene, pues, unas precipitaciones muy marcadas, pero pues para nuestro país sí son representativas. La zona del macizo colombiano, donde nacen pues, los ríos más importantes, la zona de la Amazonía, de los llanos orientales colombianos y el piedemonte llanero, pues yo estoy radicado en la ciudad de Bogotá y pues por ahí es donde entra la mayoría de humedad que precipita, digamos, en nuestro país. Y como les venía diciendo, pues en nuestro país, en nuestros países, que es Colombia, Ecuador, Venezuela, todo el centro de Sudamérica, todo Centroamérica, Brasil, pues tenemos unas condiciones muy favorables para que se presente esta convección profunda. En esta zona pues tenemos unas altas tasas de radiación, tenemos una atmósfera con un espesor más grande y se producen, pues digamos, están situadas las zonas de convección profunda. Y pues básicamente con la complejidad del terreno y las condiciones propias del trópico, pues tenemos casi que un laboratorio perfecto para estudiar este tipo de fenómenos que son muy importantes en la climatología y en la circulación climática general del planeta. Aquí, pues, en esta zona ecuatorial, se genera la celda Hadley. La celda Hadley transporta la humedad hacia las latitudes medias y ya cuando los vientos pues ya regresan a la zona ecuatorial, se genera la zona de confluencia intertropical y ahí hay un intercambio de flujos del planeta. Por lo tanto, es muy importante poderla estudiar. Y pues estamos como en ese propósito, teniendo ya las condiciones, es buscar la información para poder estudiar este tipo de fenómenos. Entonces, dentro de lo que se pueden llamar observaciones, pues está el satélite, el TRIM, que es la misión de satélites tropicales que tiene la NASA para estudiar la precipitación tropical. Es lo más parecido a lo que se podrían llamar observaciones, porque pues están midiendo, basado en un radar meteorológico que tiene un satélite, la precipitación en el trópico. Entonces, pues estas dos imágenes, una es del periodo de enero, junio, julio, y la otra es lo que es diciembre, enero y febrero, perdón, la de arriba, y la otra es julio, agosto. Pues digamos, en nuestro país lo que más incide y lo que reportan los estudios es que la zona de confluencia intertropical es lo que más incide en la producción de precipitación. Y pues eso depende, digamos, el régimen de precipitación del país va a depender mucho de la posición de la zona de confluencia intertropical. Entonces, pues en este periodo de diciembre, enero y febrero, pues la zona de confluencia está un poquito más hacia el norte, hacia el sur, perdón, y tenemos las precipitaciones más hacia el sur, y ya en julio, agosto tenemos, está más posicionada al norte. Entonces, me voy a volver un poquito a esta diapositiva. Dada esa variabilidad, digamos, de terreno, el régimen de precipitaciones de Colombia varía mucho dependiendo de esa posición de la zona de confluencia. Entonces, la zona andina generalmente tiene un régimen de precipitación bimodal, o sea, tiene dos picos en el año, y la zona más hacia el sur tiene un régimen más monomodal, un solo pico casi que todo el año es con una buena temporada de lluvias, igual que la zona ya norte de Colombia, que también tiene un régimen monomodal. Entonces, eso va muy amarrado a la posición de la zona de confluencia intertropical. Entonces, como les mostraba acá, ya está el TRIM para observar las precipitaciones en el planeta, pero obviamente esto, pues en la medida que se pueda validar con información en tierra, pues mucho mejor. Y pues ya, digamos, otro de los sistemas que tenemos para la identificación de los eventos convectivos, pues son las imágenes de satélite como el OES de la NASA. Este es un satélite que opera en todo el planeta y nos da la información de la posición de los principales sistemas atmosféricos en el planeta. Entonces, con este tipo de imágenes podemos observar muy bien dónde están digamos, la zona de confluencia, cómo se va moviendo. Podemos ver unos sistemas, por lo menos en esta época que estamos en la época de huracanes del Caribe, podemos ver cómo se van formando este tipo de sistemas y podemos incluso poder ver, obviamente con un ojo entrenado, cuáles son los sistemas de convección profunda. Pero, digamos, para poder identificar mejor esos eventos, pues con lo que está reportado en la literatura, pues hemos desarrollado un algoritmo para poder identificar eventos de tipo convectivos asociados a convección profunda, pero eso tiene que ser corroborados. Y básicamente se hace con la temperatura de brillo de esas imágenes de satélite. Y hay dos condiciones que se deben mantener para poder identificar esos eventos. Y una es que la temperatura de brillo, y básicamente lo que está midiendo los satélites como el GOES, es la temperatura de las nubes. Esa temperatura debe ser menor a 235 Kelvin. Pero aparte de eso, el enfriamiento de las nubes, el enfriamiento de esa temperatura de brillo debe ser de al menos 50 Kelvin en menos de 2 horas para que se pueda catalogar como un evento convectivo o un evento de convección profunda. Entonces, eso se da es porque los eventos de convección o de convección profunda suceden muy rápidos y se mantienen, digamos, dependiendo del tamaño de la nube, pues también va a ser la duración de esos eventos. Entonces, esa es como la condición que se ha puesto para la identificación de esos eventos convectivos. Y pues con estos eventos convectivos, pues se han obtenido unos resultados digamos, los resultados de la convección en el país. Entonces, en este caso tenemos la densidad de eventos, donde podemos observar que en esta zona del Magdalena Medio, tenemos una alta confluencia de eventos, igual que esta zona del Pacífico colombiano. Básicamente, la cordillera divide como con una frontera natural para que se presenten estos eventos. Por aquí también se ve el lago de Maracaibo, que es uno de los sitios donde más actividad eléctrica en el mundo se da, que se conoce como el faro del Catatumbo de Maracaibo. También tenemos la localización, digamos, de esas temperaturas mínimas. Simplemente, en este caso es la densidad, pero esta es la temperatura mínima, donde podemos, pues, tener un poco de eventos, digamos, más localizados. Y aquí, pues, hay que decir también que, digamos, esta metodología para poder identificar los eventos, pues, ya volviendo al operativo, pues, tiene un poco unos inconvenientes. Es que puede ser que muchos eventos se repitan, puede ser que los eventos sean suficientemente grandes y que el algoritmo los separe. Entonces toca, de cierta forma, depurar un poco la forma como se identifican estos eventos de convección. También el tamaño de los eventos y la duración de los eventos. Esas dos figuras están correlacionadas porque, pues, los eventos más grandes van a durar más. Y pues acá podemos ver todo el tema del Pacífico colombiano, donde la convección es muy fuerte, asociadas a eventos convectivos a complejos convectivos de mesoescala. La zona de lo que se llama en Colombia la depresión momposina, que básicamente es como una olla donde confluyen los ríos más importantes de Colombia, como el río Magdalena, el río Cauca y el río San Jorge. Es una, en esa zona el terreno es muy plano, pero también, digamos, se ha generado naturalmente una especie pues, de depresión, básicamente. Y ahí por las condiciones propias digamos, son complejos lagunares, hay unas tasas de evaporación muy altas y también la radiación en esa zona también es muy alta. Entonces, se da mucho para que se produzcan este tipo de eventos convectivos. Y pues esta es como una caracterización un poco más, una caracterización con el ciclo diurno de la convección, pues donde los amarillos son, digamos, los eventos que se producen en las primeras horas de la mañana, lo más rojo, es es como la zona de la final de la noche y el inicio de la madrugada, lo azul, eh, lo, los eventos un poco más hacia la mañana, casi sobre el mediodía. Ya lo azul más oscuro es como la zona de la tarde, que pues digamos está muy correlacionado con la temperatura del suelo. Y lo rojo, lo magenta es digamos ya las horas de la tarde-noche. Entonces podemos ver que el ciclo de la precipitación o de los eventos en el país también tiene una alta variabilidad en el ciclo diurno de esta precipitación. Entonces, eso es lo que nos ha permitido poderlos estudiar con digamos ya para verlo un poco más en Bogotá, esto se hizo, digamos, esto se hizo fue con imágenes del GOES 13. El GOES 13 pues tiene información desde 1998 hasta el 2017, entonces eso es como el periodo de estudio. Y se hizo, digamos, el GOES tiene una resolución de 4 kilómetros. Lo que se hizo fue aglutinar esos eventos en una resolución un poco más gruesa para poder ver otros eventos para la ciudad de Bogotá. Entonces aquí tenemos el ciclo diurno, donde en la ciudad de Bogotá se presentan muchos eventos en las horas después de la 1 de la tarde empiezan a subirse los eventos. Pues obviamente esto va a depender mucho también de la temporada de precipitación, pero pues lo que marca, digamos, la información que se puede obtener con el GOES es que tenemos muchos eventos en las horas de la tarde, pero también tenemos ciertos eventos pues, de cierta importancia en las horas de la madrugada. Y como les venía diciendo, pues esta gráfica de abajo lo que describe es digamos, la climatología de Colombia, de Bogotá básicamente, donde se tienen dos picos y eso está muy influenciado por la zona de convergencia intertropical que varía dependiendo de la época del año y pues obviamente con las imágenes GOES podemos observar que se pueden ver esos dos picos eh, muy bien definidos. Pues yo no lo dije, pero Bogotá queda muy hacia el centro del país, queda en una meseta que es lo que se llama la sabana cundiboyacense, en la cordillera central. Entonces, digamos, tiene unas condiciones muy particulares porque está muy influenciada por el Valle del Magdalena, a pesar de que, o sea, digamos, está muy cerca del Valle del Magdalena y también de la zona de la Amazonía. Entonces ahí vamos a tener, digamos, dependiendo de la hora del día y de la época del año, pues vamos a tener una influencia climática diferente en esta ciudad. Y pues la otra zona que estamos estudiando es la zona se llama la zona de la Mujana o la depresión momposina, que queda pues, en la zona en las que decía que concluyen los ríos más importantes. Bueno, esta gráfica me quedó un poco invertida. Voy a empezar con la parte del ciclo diurno de los eventos convectivos, donde en la ciudad de Bogotá los teníamos más entre 2 y 6 de la tarde. Aquí se corre un poco más los eventos convectivos, pero tenemos también unos fuertes, o sea, tenemos muchos eventos de tipo convectivo en las primeras horas de la mañana. Entonces, pues esto está muy influenciado también por la zona, por el fenómeno de brisa marina, por lo que está muy cerca del Caribe colombiano. Y pues eso es lo que también vamos a estudiar en este estudio sobre los eventos de convección en la zona de la Mojana. Y acá pues, como para ya ir como explicando el tema del vapor de agua y el tema del vapor de agua precipitable es una variable muy importante, pues es básicamente el insumo clave para la producción de precipitación, y pues lo tenemos en unos porcentajes más disponibles en la zona del trópico. Pero también el vapor de agua varía mucho en altura, en la vertical. Entonces, en la medida que uno suba más, el vapor de agua se va haciendo más escaso, y el vapor de agua es uno de los principales gases de efecto invernadero que tiene el planeta. Y pues hay algunos mecanismos para poderlo observar. La NASA con su satélite OES tiene un sensor para poder observar el vapor de agua. Es muy importante para poder estudiar estos eventos convectivos y poder hacer, digamos, en el tema de pronóstico operativo, empezar a mirar cuáles son los sitios donde se va acumulando más vapor y pueden haber precipitación. Esto lo cuento es porque, digamos, se empezó a trabajar con una red de sensores del sistema de navegación global, de los GPS. Esto lo usan mucho los servicios geológicos de los países para poder hacer la trazabilidad de las tectónicas de las placas, también para hacer seguimiento a las fronteras y ese tipo de cosas. Y lo que se dieron cuenta con este tipo de sensores es que cuando la atmósfera está muy saturada de vapor o tiene mucho vapor, empieza a hacer que las señales empiezan a tener como unas especies de errores. Y empezaron a mirar que la señal se atenúa, o sea, pierde fuerza la señal cuando la recibe. Empezaron a crear una serie de algoritmos para poder filtrar esa señal, y se dieron cuenta que lo que son esos errores es básicamente lo que es el vapor de agua de la atmósfera. Y esa información se empezó a aprovechar en temas de meteorología. Es una información que está a unas resoluciones temporales muy altas, o sea, eso está incluso por debajo del segundo. Eso se mide casi que en continuo. Obviamente pues no es en continuo, pero se podría decir que es casi en continuo, y es de mucho valor en la atmósfera. Pues digamos, no vamos a tener la información discretizada en la vertical, o sea, no vamos a tenerla por capas, porque se tiene como todo el valor de la columna de vapor, pero sí se puede ver la evolución en el tiempo. Entonces, es una información de mucho valor, y esta información, digamos, la mayoría de países tienen una red de sensores instaladas para hacer el seguimiento del territorio, o sea, básicamente de la capa de suelo y la tectónica de placas. En nuestro país, en Colombia, pues tenemos una red que cada vez se va volviendo más densa, y pues dada como digamos, ese aporte que puede darle la meteorología, y pues que se necesita también, pues para ellos es un error. En el caso de nuestro país, el Servicio Geológico Colombiano es el que maneja la red de este tipo de sensores. Para ellos es un error en la señal, pero es muy útil para la meteorología. Entonces, generalmente donde instalan un sensor de estos, instalan una estación meteorológica. ¿Para qué? Pues digamos, ellos no la necesitan, pero sí se han dado cuenta que es muy útil, entonces la instalan, y para poder calcular y volver esa señal digamos, de ruido blanco en los sensores GPS, pues se requiere una información que es la presión atmosférica y la temperatura ambiente. Entonces, generalmente en Colombia, sobre todo, pues en otros países, yo me imagino que también, donde se instala un sensor de esos, se instala una estación meteorológica y ahí se va convirtiendo esa señal de ruido blanco ya en lo que es el vapor de agua en la atmósfera. Entonces, en nuestro país, pues tenemos ya una red cada vez más densa, cada vez se instalan más estaciones de estas. Para ellos es muy útil para hacer el seguimiento al tema de sismos y eso, y para nosotros los meteorólogos también. Entonces, esa información se va haciendo más útil, esa información del vapor de agua se puede asimilar en los modelos de pronóstico, entonces vamos a tener una información de inicialización de esos modelos un poco más acordes a la realidad y eso nos va a permitir que los pronósticos sean un poco más acertados. Y para el tema, digamos, de aplicaciones en la convección, pues ya hay unos estudios y pues acabo de mostrar como de los más relevantes para la convección en la zona tropical y es la que ha hecho Adams en la zona de la Amazonía. Pues ellos usaron más o menos 3.5 años de datos de los sensores, la información de los sensores, pues esto puede estar incluso, como les decía, en una resolución temporal por debajo del segundo. Pero pues ellos, eso se maneja estadísticamente porque pues, hay mucha información para manejar, entonces la manejaron cada 30 minutos con la información de estaciones meteorológicas cada minuto, las imágenes GOES y pues de cierta forma pudieron identificar 320 eventos convectivos. Pues aquí ya es donde pues, uno empieza a encontrar ese tema de los patrones meteorológicos y es que es cuando se empieza a cruzar esa información en este caso, la gráfica verde es lo que se llama la columna o el vapor de agua precipitable junto con la temperatura de la nube, en este caso sacada de las imágenes del satélite GOES, y con la información de la precipitación. Esto se hace, digamos, se centra, se pone un cero como falso para poder estudiar esta información. Y pues se han encontrado, pues digamos, señales muy fuertes de cuando se empiezan a presentar esos eventos convectivos. Entonces, cuando uno empieza a echar para atrás un poco, puede encontrar, digamos, las señales de ese inicio del proceso de convección. Entonces es muy importante poder cruzar esa información y tener información de buena calidad y buena resolución para poder encontrar estas señales. En este caso, pues Adams encontró señales de convergencia o de convección débil a las 8 horas. Digamos, acá es cuando empieza uno a ver unos pequeños cambios de pendiente, pero ya cuando la convección se empieza a poner intensa o la convergencia de corrientes se empiezan a poner intensas, las empieza a encontrar a las 4 horas. Pues esto es muy importante, poder tener estas características y estos patrones meteorológicos, porque a la hora de implementar este tipo de metodologías en sistemas de alertas tempranas, pues uno sí le puede ganar mucho tiempo a la precipitación. Para el caso de Bogotá, pues tenemos información, esta es como la estación más antigua de Colombia, pues ya tiene cerca de 20 años de datos y podemos ver que la información de la columna de vapor de agua extraída de los sensores pues coincide mucho con el ciclo diurno de la temperatura y pues obviamente también coinciden con el ciclo diurno de la precipitación, donde empezamos a ver que los valores más bajos o más altos de vapor de agua empiezan a ocurrir después digamos, del mediodía y pues tiene una leve variabilidad a lo largo del día. Esta estación queda en la universidad también donde yo trabajo, en la Universidad Nacional. Está colocada allá y pues ahí también hay una estación meteorológica digamos, en tiempo real. Lo importante es que haya información de las estaciones meteorológicas que midan casi en tiempo real, por debajo, ojalá, de la hora, para que se puedan ver estos eventos convectivos, porque la iniciación de estos eventos convectivos pueden ser de pocas horas. Entonces, ojalá, pues, si no se tiene por debajo de la hora, que sea por lo menos en una resolución temporal horaria. Y pues cuando se ha comparado ese vapor de agua con las variables, pues esto es una reconstrucción del vapor de agua, pues, de los radiosondeos. Este es el radiosondeo de la ciudad de Bogotá. Pues vemos que coinciden muy bien y conserva la tendencia del comportamiento del vapor de agua. Y este pues es uno de los casos que estábamos estudiando en la ciudad de Bogotá, y es en la primera imagen es el vapor de agua precipitable versus la precipitación, donde también se pueden ver, digamos, muy claras señales con la información de esta variable para el inicio de este tipo de precipitaciones, y se puede empezar a caracterizar las horas de inicio de la convección. Bueno, este es un error ahí con la temperatura. Y también, ¿qué pudimos encontrar? Digamos, acá se están mostrando los resultados más relevantes. Empezamos a encontrar una serie de patrones a la hora de los casos de convección en la ciudad de Bogotá, y pues eso lo vamos a replicar para la zona de la Mojana. Y es que hay cuando se empiezan a presentar este tipo de eventos de tipo convectivo, por lo menos en el caso de la dirección de viento, se pudo observar que cuando hay un cambio de viento abrupto, en el caso de Bogotá, cuando pasa el viento que viene del norte hacia el viento de occidente, pues es porque viene un evento convectivo. Y también se pudo observar con el tema de la velocidad de viento. Hay una aceleración muy fuerte del viento, obviamente porque está arrastrando mucho vapor de agua, y apenas empieza a precipitar, se empieza a bajar esa velocidad de viento. Entonces, la información, digamos, con este tipo de observaciones es muy útil, y como les decía, pues tenemos la información. Seguramente en Ecuador también van a tener ese tipo de sensores de la red de posicionamiento global. Está la información, es gratis porque está ahí, es un error para los servicios geológicos y se puede usar en muchas aplicaciones de meteorología. Y pues eso es lo que les tenía para contar digamos, de los sistemas convectivos y la convección profunda. Y pues aprovecho esto para darle un agradecimiento al profesor Daniel Hernández Díaz, que es el coordinador de la maestría de meteorología de la Universidad Nacional, con el cual se han estado explorando este tipo, digamos, de tecnologías para meteorología. Entonces, si tienen alguna pregunta, pues estoy atento.
Muchas gracias, ingeniero Hugo Rico. Sí, tenemos unas preguntas y también estamos aceptando las preguntas en el chat o en la sección de preguntas y respuestas, QIA. Bueno, la primera pregunta la hace Mabel. Dice, buenas noches. Ya que el satélite TRMM salió de órbita hace varios años, ¿de dónde obtiene la información satelital de precipitación?
Bueno, la información del TRIM nos sirve simplemente para verificar los eventos de convección, para verificar la precipitación. Entonces, esa información pues no la usamos mucho, usamos más la información de las estaciones meteorológicas, pero se usó la información del OES 13, también salió de órbita, pero se están haciendo estudios con la información que recolectó desde 1998 hasta el 2017. Entonces, como les digo, pues el TRIM es como para verificar si la información de las estaciones pues está bien. Y en la medida pues que vayamos actualizando, pues tenemos que buscar, digamos, otro tipo de información satelital para poder verificar este tipo de eventos convectivos.
Ok, muchas gracias. La siguiente pregunta dice, ¿cómo descarga la información de PM, medida global de precipitación?
Bueno, la información de los satélites es un poquito tediosa porque está un poquito, o sea, no se puede hacer como un algoritmo se pueden bajar, pero por paquetes. Eso se baja directamente, digamos, de las páginas de la NASA. Somos afortunados porque la mayoría, digamos, de la información que se tiene de satelital, sobre todo de las agencias de Estados Unidos, está de forma libre y pues incluso ellos generan los mismos algoritmos para poderla descargar. Entonces lo que nosotros hicimos fue descargar todo el periodo de 1998 a 2017 para poder hacer estos estudios.
Ya, muchas gracias. Voy a revisar si hay más preguntas. Ok, al parecer no hay más preguntas. Gema, ¿tú ves si tienes más preguntas, por favor?
No, al parecer no hay más preguntas.
Bueno, pues muchas gracias por la invitación.
Muchas gracias a usted, Máster Rico. Agradecemos su tiempo. Muchas gracias por esta charla.
No, con mucho gusto, muchas gracias por la invitación y pues estaré atento a cualquier requerimiento si requiere más información al respecto o se requiere hacer otra charla que tenga que ver con esto cuando tengamos más avanzadas las investigaciones.
Muchas gracias. A todos los participantes también quería decirles que la siguiente charla va a ser a través de Google Meet y les acabo de poner el link en el chat para que por favor puedan unirse. No será aquí en Webex, será en Google Meet. Y ahorita les puse el link de la charla a través del chat. Esperamos verlos allá y muchas gracias.
¿Me puedes reenviar el link? Porque han escrito que no lo ven. Por favor.
Ok, ya lo envío.